Alright, so what I'd like to do tonight is just take you through a couple of example problems. The first one's just going to be a problem involving torque. The other one is going to be looking at mechanical equilibrium. And so we'll do that, and then I'll do a couple of other videos that go through other example problems that will hopefully help you to be able to do the problems tonight. Now I want you to be able to focus on not just the fact that we're putting numbers into equations, but also conceptually what's going on, because that'll help you to understand the conceptual ideas of torque. Alright, so in this first problem we've got a door that we're viewing from above, right? So we've got several forces acting on it. We've got one acting right at the pivot point, we've got one right here, one out at the outside, and then one very far on the edge of the door which is pushing it at an angle. Alright, so we're going to find the torque of each of these. Alright, and then we'll add them all together. Now keep in mind that anything that causes your radial arm to go clockwise is going to be a positive torque. Anything that causes your radial arm to go counterclockwise is going to be a negative torque. Alright? So let's go ahead and look at it. This first one, the radial arm is 0. Remember, your equation for torque is the length of the radial arm times the force times sine of the angle. Right? Now if you look at this one, the radial arm, or the distance from the pivot point to where the force is being enacted, is 0. And so the torque of this one is actually going to be 0. And I can do that without doing any calculations. Alright, let's go ahead and look at the next one then. So the torque of this one is going up at 50 newtons. It's a right angle to the arm, so there's your radial arm right there. It's 0.2 meters, and so let's call this one torque 1. So torque 1 is going to be equal to the radial arm distance, which is 0.2 meters, times the force, which is 50 newtons, times sine of theta, alright, which is 90. Okay, we know that sine of 90 is 0. 0.2 times 50 is going to give me a torque of 10 Newton meters. Okay, now you can get the negative in two ways. Number one, you can consider the fact that the force is going to cause your arm to go counterclockwise, and so that's a negative force. Or you can just say, okay, well, in the end, I know that this force is going to cause my door to open upwards, which is going to be counterclockwise, which is negative. So this is going to be a torque of negative 10 Newton meters. Alright, let's go in and do the next force then. Alright, so the next force has a radial arm that goes from the pivot point, 0.2 meters, and then another 0.6 meters. Alright, so if we call this torque 2, that's going to be equal to a total radial distance of 0.8 meters times the force, which is 70 newtons, and then times the sine of theta, which again is the sine of 90, which is 1. So you multiply those, and you get a torque of 0.8 times 70. So let's go 0.8 times 70, which is 56. So we've got a torque of 56 Newton meters. Okay, now this one again, you can say, well, my force is going to push my radial arm in a clockwise manner, so it's a positive force. Or you can look at it and say, well, that means that once I look at the direction of the force, it's going to cause my door to go in this clockwise direction, so it's going to be a positive torque. Alright, so now let's look at the last torque. We'll call it torque 3. Okay, now we've got the full length of the door, which is a full meter. So the radial arm will be 1 times the force, which is 80 newtons, times sine of 30. Now remember, the angle has to be the angle between the force and the radial arm. Okay, again, this force is going to be pushing my door in a counterclockwise direction. So I know in the end it's going to be a negative force. But let's go ahead and do 80 times sine of 30, which is going to be 40. And so my torque 3 is 40 Newton meters. Alright, negative because it's going counterclockwise. So if I want the total torque, then I'll add them all together. So that's negative 10 plus 56 minus, bless me, minus 40 Newton meters. And so I add all those together, and I get a total torque of 6 Newton meters. All right, so hopefully that makes sense. It's positive, which means that the door will open clockwise, which would be down. So there you go. There's your first example. Let's look at one that's going to balance mechanical equilibrium now. All right, this time I've got a meter stick, which has a mass of 0.15 kilograms. It's supported at the 50 centimeter mark. So let's go ahead and draw it. Okay, drawings are going to be absolutely essential for this unit with torque. I mean, they were important before, but even more now. So here's my 50 centimeter mark. I'm going to go ahead and label this as 0. And then since it's a meter, this will be 100. Now I know that the stick has a mass of 0.15 kg. A mass of 0.5 kg is attached at the 80 centimeter mark. So here at 80, then I'm going to need to put on a mass of 0.5 kg. Now that's not a force, right? That's just the mass, but I'm going to write it down there for now. All right, so A, how much mass should be attached to the 40 centimeter mark to keep the meter stick horizontal? So here's my 40 centimeter mark. And how much mass do I need to put there? Now, you should be able to kind of go through this conceptually, right? We know that there is a specific relationship between the force and the distance, an inverse relationship, right? So as I go farther out, then I need less force. As R gets bigger, F gets smaller. Needs to be smaller in order to exert the same torque. So if I have a certain amount of torque here, which is 30 centimeters away, the torque going to be necessary here needs to be the same in order to balance, right? Because I've got this one that's going down or clockwise. This one will be going down, which will make my meter stick go counterclockwise. So since it's a third of the distance, we should expect that the mass should be 3 times as big, right? Well, let's go ahead and check. Okay, so we're going to look at two things. We're going to balance both. Let's go with the torques. Okay, so we're going to add together all the torques. So the torque here is going to be equal to the distance from the point of rotation, which is going to be 30 centimeters, 0.3, times the force, which is 0.5 kilograms times 9.81, right? So 0.5 times 9.81 times sine of theta. Now since it's going straight down, we're going to say that sine of theta is sine of 90, which is 1. All right, now that one's going this way, which will cause my meter stick to go clockwise, so that will be a positive torque. And then over here, I'm going to need another torque, so torque 2, which is going to be equal to the radial distance will be 10 centimeters here, so 0.1 times the force, which is going to be the mass times 9.81, times again the sine of theta, which will be 1 again. Now in this case, it's going down, which is going to cause it to go counterclockwise. So this is going to be a negative torque. Okay? So now, if I want it to be at equilibrium, if I want it to balance and stay horizontal, then the sum of the torques have to be equal to 0. All right? Which means that when I take these and I multiply those together, so 0.3 times 0.5 times 9.81, which is 1.47 Newton meters. And then if I do the other one, so 0.1 times 9.81, so 0.981 m, so negative 0.981 m. So if I rewrite that, adding the torques together, so I've got torque 1 plus torque 2, so 1.47 minus 0.981 m should add together to give me 0, because the torques have to balance. And so let's go ahead and solve that. So we're going to subtract the 1.47 to the other side, so negative 1.47 divide by the negative 0.981, and we're going to get a mass of 1.5 kg, which, what we said earlier, Remember, we said since the distance was a third, then we needed a mass that was triple. All right? So that's the case. Now the second part of the question says determine the supporting force from the fulcrum on the meter stick. So with how much force is the fulcrum having to push up, or the normal force of the fulcrum? Now to get that, obviously, for our meter stick to be in equilibrium and not dropping, all the forces have to be equal. So now we're just going to look at all the forces acting on the meter stick, right? So we've got the mass right here, the 1.5 kilogram mass. So that's going to be one force down. So we're going to go sum of the forces equals 1.5 times 9.81. Now that's down, so we're going to call that negative. And then we've got the other mass, which is pulling down. So that's going to be minus mass times 9.81. Now we can't forget the mass of the meter stick, right? The meter stick is 0.15 kg. So, oops. Meter stick is 0.5 kg, so minus 0.15 times 9.81. That one's down as well. And then the only other force acting on our meter stick here is the normal force of the fulcrum, so plus the force of the fulcrum. Now we know that since it's balanced, and since it's not moving up or down or accelerating up or down, that the sum of the forces equals 0. And so from that point we should be able to solve for the force of the fulcrum. So let's go ahead and do that. So we got 1.5 times 9.81 plus 0.5 times 9.81 plus 0.15 times 9.81. And there you go. 21.1 newtons. So the force of the fulcrum has to be equal to 21.1 newtons. There you go. We've answered the question using both the balanced torque and the balanced forces, which means that it is in mechanical equilibrium. All right, I hope you'll take time to watch the other two videos and see the examples there.